Chapter 14 discusses acids and bases. In sections 14.1 through 14.3 and bringing in section 12.2, we're going to have an introduction to these concepts of acids and bases in this video. We can categorize acids and bases in three ways and by three definitions. The most common one that you have already heard through this definition of neutralization reaction is that an acid contains hydrogen ions and a base contains hydroxide ions. This is from the Arrhenius definition of what an acid is and what a base is. It's a very elementary description of acids and bases, and it holds true for many substances that are acids and bases, but it's limited in its scope. Bronsted-Lowry definition, and that's purposely an O with a slash, it's a different character, not in our alphabet. Bronsted-Lowry definition of an acid refers to it being a proton donor. And the definition of a base, according to the Bronsted-Lowry definition, is that it is a proton acceptor. So if we think of what a proton is, a proton and a hydrogen atom both have one proton in hydrogen and a proton. So the Bronsted-Lowry definition defines acids and bases in terms of protons. Even that definition is limited in its scope. And when we get to, well, we won't get to it in this class, but when we get to organic chemistry and we need to define acids and bases, the Lewis definition is the one that covers most substances. The Lewis definition of an acid is that it is an electron acceptor, and the Lewis definition of a base is that it's an electron donor. So in this course, we primarily focus on the Arrhenius definition. In Chem 122, focus more with this definition, and even in this course a little bit. And then in organic chem, you focus more on this definition here for acids and bases. But we're going to see how these definitions cover the substances that we're going to look at. Some acids contain more than one hydrogen ion, and they are called polyprotic acids. All right, I'm going to take some common household substances and just to show you that which ones are acids and which ones are bases by a simple litmus paper test. Now, we had said in the previous slide that acids will turn blue litmus to red, and bases will turn red litmus to blue. Bases end up blue, BB, bases blue. So let's look at some substances I have here. I have homemade orange water. I really would say orange juice. I have Coca-Cola. I have bottled water. I have Windex with ammonia, and I have bleach. And I have two pieces of litmus paper, one blue, one red. Now, we said that foods are typically acids. So let's see. Does the blue litmus paper stay blue or turn red? It turned red. Acids end up red. Does the red litmus stay red? Yeah. So oranges contain citric acid, okay, ascorbic acid, vitamin C. Blue litmus turns to red. Okay, now let's look at Coca-Cola. Coca-Cola has phosphoric acid right in the ingredients right there. Okay, Pepsi-Cola too. Mountain Dew also. Let's see. Does the red stay red? Okay, looks like it does. Does the blue turn to red? Yes, it does. So we have two acids right here. The orange juice or orange water, and Coca-Cola. All right, let's look at the regular bottled water. Okay. Now, not everything is an acid or a base. Some substances are neither. Well, the blue stays blue and the red stays red. Neutral, neither acidic or basic. Let's go to Windex. Now, cleaning products typically are bases. So we should see the red turn to blue and the blue should stay blue. The red went to blue, the blue stayed blue. Let's look at bleach. Regular household bleach, I'm going to pour some in the cap. Bases end up blue. Well, that red went to blue very quickly. So we can see food products tend to be acidic, water is neutral, cleaning products typically are bases. Okay. Let's look at how we name acids and bases. Let's start off with naming acids. We have two categories of acids that we're going to learn how they are named. Binary acids consist of hydrogen ions and a monatomic ion, anion. Okay. For these types of acids, for the binary acids, we have a hydro prefix and then an ic acid ending. Common binary acids, HCl, HBr, which are called hydrochloric acid, okay, from the chloride ion, hydrochloric acid, and hydrobromic acid, bromide ion, bromic, hydrobromic acid. You don't have that many binary acids. You have hydrosulfuric, you have hydroiodic, hydrofluoric. Okay, hydrochloric acid is the acid that's in our stomachs that aids in digestion of our food. It's a very strong acid, and we'll talk about strengths of acids in a little bit. But it's also a common acid that we use a lot in lab. Oxyacids are acids that consist of hydrogen for the cation and a polyatomic ion that contains oxygen. So the polyatomic ion contains oxygen. With the oxyacids, we do not have the hydro prefix. So there is no hydro prefix when you have an oxyacid. And the polyatomic ion that comprises that acid, if it ends in an ITE, if it's an ite ion, it makes the acid ending OUS. So itis. If it's an ate ion, ends in ATE, nitrate, sulfate, phosphate, it becomes an ic acid. So ite ions become OUS acids, ate ions become ic acids. Nitrite would become nitrous acid. Sulfite would become sulfurous acid. Nitrate with an acid would be nitric. Sulfate would become sulfuric. Phosphate, when it becomes bonded to form an acid, would be phosphoric. Here are two examples here that I have mentioned. Hydrogen combined with the nitrite ion forms nitrous acid. Hydrogen with the nitrate ion forms nitric acid. Okay. The nitric acid is it's an acid that's used to help determine if a metal sample is real gold. A lot of times people are trying to get money for some scrap gold. They'll take it to a jeweler or some dealer of that sort, and they will take a little bottle and they'll take a drop and they'll apply it to the metal. And the bottle is a solution of nitric acid. I'm not sure what the concentration is. But basically, if the substance, the sample, the metal sample, if it's gold, gold doesn't react with the nitric acid very quickly at all. But the other metals, such as silver and zinc and copper, okay, nickel, would react readily with the nitric acid, and therefore would be a determination that that piece of jewelry is not real gold. Let's look at a couple more common acids that are binary acids and oxyacids, just to have them down in, so, because if we come into, you know, if we read about them or we see them in, you know, in the lab manual or future courses, we know what their names are. So I'm going to give you a list of common binary and oxyacids in addition to what I have written here, and then we'll go into naming bases. Some other common acids. Binary acids, I mentioned hydrofluoric acid. Hydrofluoric acid is used to etch glass. Binary acid consisting of hydrogen and the fluoride ion. Some other common oxyacids, sulfurous acid and sulfuric acid. Sulfuric acid is the acid that is in batteries, whether it's a car battery, some of your small batteries for electronics, like your AA and AAA batteries, but definitely your car batteries have sulfuric acid in there. Phosphoric acid is used in different food products. It's actually an ingredient in Coca-Cola and Pepsi Cola. You can look at the ingredients and you'll see that that's there. I believe its purpose is a preservative, but I might be wrong. Don't quote me on that. Okay, acetic acid is the acid that is in vinegar. Okay. If we look at the first three acids here, they are polyprotic acids. They have more than one hydrogen, more than one proton part of their structure. So these would be polyprotic acids right here. Let's go now into naming bases. Bases consist of typically a group 1A or 2A metal cation and the hydroxide ion. Okay. These are for the Arrhenius bases. How do we name these? We already know. When we learned in chapter 6 how to name compounds, okay, this is just like naming an ionic compound. You name the metal cation first and you name the hydroxide ion second. This compound right here is a base. It's the active ingredient in Phillips milk of magnesia. Magnesium is the metal cation. Hydroxide is the anion. Magnesium hydroxide. Next substance, calcium hydroxide. Calcium hydroxide is the ingredient that is put into orange juice to make the orange juice be calcium fortified. Naturally, orange juice does not have calcium in it. So this base is added to give it calcium. So it's put in there synthetically. And this is the source of that calcium ion. You know, the next substance is used to make soap. It is in oven cleaners. It's in liquid Drano, liquid plumber. The cation is sodium. The anion is the hydroxide anion. So it's very simple to name the bases, okay? Nothing new there. Strengths of acids and bases. How do we define that an acid or base is strong or not? Qualitatively, we can describe the difference based upon dissociation. We're going to learn how to do it quantitatively in a little bit. But right now, just description, qualitative. Acids and bases dissociate or separate into their respective ions in water. How strong an acid or base is depends upon the extent of the dissociation of the acid or base and the subsequent amount of ions. Take, for example, this illustration. This illustration here depicts a strong acid or a strong base, and this illustration here depicts a weak acid or a weak base. In the pipette, you have 5 molecules of either a strong acid or a strong base. Okay, red and blue colors representing either the cations or the anions of that acid and base. When you have a strong acid or strong base, all 5 of those units break apart into their respective ions, as you can see by the separate blue and red dots representing the ions making up the strong acid or the strong base. So 5 units of strong acid or strong base, and the subsequent amount, 100% of breakdown for that strong acid or base. Complete dissociation and formation of ions. In contrast, when you have a weak acid or a weak base, you only have partial ionization occur. So let's say we have 5 units in the pipette represented by the blue and red dots, 5 units of either a weak acid or a weak base. When you put it into a solution, when you put it into with water, okay, what happens is that you have some of those units separate and some stay intact, as represented in the picture here. So we have 5 units of some weak acid or some weak base, and 3 of them stayed intact as that molecular acid or base. And the other 2 units split apart into their respective ions. So when you have a weak acid or a weak base, you have some amount of ionization, but not complete ionization as you do when you have a strong acid or a strong base. Let's examine further the strengths of acids and bases. I had that picture up that showed strong acids and bases versus weak acids and weak bases in terms of dissociation. And let's just write that description into words. So strong acids and bases completely dissociate into their respective ions. They're also strong electrolytes, okay, because of the high ion content in solution. Remember that one lab where we had to determine electrical conductivity, and these terms, electrolyte, strong electrolyte, weak electrolyte, and non-electrolyte came up? We're going to fit them into our discussion now. Strong electrolytes, you have high ion content in solution. So strong acids and strong bases are strong electrolytes. I gave you an example in the picture where I said it's a strong acid or a strong base, you have complete ionization. Hydrochloric acid, you have 100 units of hydrochloric acid. All 100 units would break apart into the hydrogen and chloride ions respectively. You'd have complete ionization. You have high ion content. You have a very strong electrical conductivity. And we saw that in lab. Remember when we used the conductivity meters, you were getting the error readings for this acid in particular. It was such a high conductivity value that the meter couldn't even register it. Another example of a strong base, which is also a strong electrolyte, is sodium hydroxide. If you had 100 units of sodium hydroxide, all 100 units would break apart into the sodium ion and the hydroxide ion. You'd have complete ionization, high ion content, strong acid, strong bases, strong electrolyte. Let's go down and talk about weak acids and weak bases. The picture I had previously up showed an example which would illustrate a weak acid or weak base. You have partial dissociation into their respective ions. Each acid is different into how much it dissociates into its ions. We're not going to worry about that for this course. That would be for a later on course where you would actually do calculations to determine those quantities. But you have partial ionization. Weak acids and weak bases are also weak electrolytes because you have a lower ion content in solution. You still have some amount of ionization occur. So because you have charged atoms, which are ions, you do have some electrical conductivity that can be transmitted through that solution. Let's look at an example of a weak acid. Acetic acid, the acid that's in vinegar. If you have an aqueous solution of acetic acid, and you have 100 units, let's say, in theory, of acetic acid, only 5 out of 100 units would break apart into the hydrogen ion and the acetate ion. The other 95 would stay intact as molecular acetic acid. So 100 units, only 5 break apart. That's a weak acid, okay? And weak bases, an example would be ammonium, there's some other ones too, but so that's to categorize strong acids and bases versus weak acids and bases. Well, what about those substances that are neither? Non-electrolytes. Non-electrolytes are solutions that do not contain ions, therefore do not conduct electricity. Now, just to make sure that we have a clear understanding of electrolytes, Remember, electrolytes are solutions that conduct electricity due to having a presence of ions, which are charged atoms, okay? And if they have a lot of ions, strong electrolyte, a little bit amount of ions, weak electrolyte, no ions, non-electrolyte. And prime examples of solutions that would be non-electrolytes would be sugars and alcohols. Sugars like glucose, sucrose, fructose, and alcohols like methanol, ethanol, isopropanol. So these substances would do not contain ions, therefore they do not conduct electricity. Likewise, they are neither strong acids or strong bases, and most times a lot of them are not even weak acids or weak bases, but that depends upon what the actual sugar or alcohol is.